I think, of the previous talk about some of the issues that we face. I think I've been in some of the positions as being sort of the leader who then sort of frowns upon some of the things that we see. And so let me give you a little bit of an insight for differential privacy specifically. This might get somewhat controversial, hopefully not, but the point is to drive more discussion. Right, so first, kind of, again, on the credentials, since not everybody knows everybody. So I've been doing differential privacy and privacy at Google for about 6 years. We've built a bunch of different systems that do differential privacy at scale. We've published surveys on how to do it for machine learning. We've been delving into synthetic data and LLMs with differential privacy, and so on and so forth. Right. So before we begin, since there's a lot of differential privacy people here, we're going to do a little survey. Right. Your data is about to be shared. You have no choice. You have two options here. You can choose to go with canonymity, or well-loved canonymity with k equals 10. This is terrible. Or you can go with differential privacy with epsilon equals 10. So think for a second, where would you like to land? And then we'll do a show of hands. We're not going to do this privately. So for canon, 1. Differential privacy, 15. All right, we'll get back to this.
Well, it depends on what you're doing. Like,
This is what you get,
okay.
right? To Shannon's point, like you have a method, and these are the techniques, these are the trade-offs that you have. Okay, so my view is actually slightly different from the previous speaker. Is that the promise of differential privacy was that we don't need to think in a multidimensional way, right? We have this one parameter. This one parameter really captures the critical guarantees that we're providing. This is the definition that we have. It's a worst case definition. It doesn't allow for the people to come after and say, oh, here's an attack that you didn't think of, whether it's homogeneity, whether it's something else, right? And this is something that we can focus on. And this was the real promise overall, right? It's the rigor and the ability to then also academically to write papers and say, mine is better than yours because I can get the same utility at a lower epsilon, right? Whereas if you have a vector, you can't really do these kind of bragging claims overall. So this helps. So let me give you 3 reasons of where we've kind of landed up. Of course, we start with sort of a picture. There's theory. Theory is never this way. But this practice, I would say, is reasonable, right? The practice that's unreasonable is that there's just a pile of dogs all chasing each other. We're not there. But what are the kind of the differences where we ended up? Okay, so 3 stories. So first story is on sensitivity, right? Sensitivity is key to differential privacy. This is an easy thing to say, right? And we're going to take this simple example of computing just a private sum. Right. There's 2 distinct issues that are going to come up if you do this in practice, if you build a system for computing private sums. So it could be that a single individual is an outlier in 2 different ways. One is you have a billionaire in the database of college dropouts, you're looking at their income or you're looking at something else, right? And somehow Mark Zuckerberg is one of them overall, right? And so now you have 2 options. You either need to clip and sort of limit the value that he provides, or your sensitivity is very high, right? This is a usual bias variance trade-off that we'll talk about, but this is a real trade-off. That's it. The second part is that a user could contribute many different values, right? So we talk traditionally about kind of there's a record in the database, 2 databases are adjacent if they differ in a single record, but of course this is not the case, right? If I look at search queries, if I look at people driving, if I check like congestion pricing that just got introduced in New York, taxi drivers are way more affected than regular commuters. They're just in a different class, right? So what do I have to do here? I also have to restrict the number of sort of records that a single individual contributes, and then I can talk about sensitivity and everything's bounded and everything's good, right? Simple solutions, not much to do. So 2 questions. One is from a utility standpoint, there may not actually be a good count, right? It is a bias variance trade-off, but it could be that either the bias or the variance is terrible in whatever that you do, right? If you have a heavy tail distribution, you can write this formally, it is actually going to be terrible. Now you can come back and say, Sergei, you shouldn't be computing means in that case. Mean is a bad statistic, you should be computing medians, but people compute means, this is what they want to do, this is what they're familiar with, so sorry, your objection doesn't apply. For DP guarantees, again, any cap is okay, this is a free parameter, but how did you pick it? And I bet you peeked at the data, right? Because everybody does, right? How many, like, what is the average kind of salary that we're looking at? How many things are here, etc. You shouldn't be allowed to do that. That goes against the privacy guarantees that you have, right? So what happened, right? Why are you not counting that part? Whereas you should be. Now, I should say there are papers that say how to do this privately. So there is work in that direction, and I don't want to diminish it, but this is a problem. Overall, this is a problem that we encounter almost every single day. The bigger problem, I think, goes back to Shanan's point, is that now I have a trade-off. If I want to look at the second question, where I'm limiting the number of times a user contributed to the data set, I have to store user information together with every single one of my records. I can no longer just store and say, here's the records, here's the times that, you know, a car passed through congestion pricing. I have to say, this car passed through congestion pricing, so that later on, when I'm doing my DP analysis, I can actually limit and remove some number of cars to limit my sensitivity so I can get practical guarantees. This is a terrible thing, right? Because we all know that if you have sessionized data where you can link different information about users, this is going to reveal a lot more information, right? So now you have a very stark trade-off as a policymaker, right? Do I want to have user level differential privacy with real bounded sensitivity at the cost of storing user IDs when I have this database? Or do I forego that and I have more record level privacy, but I don't store these IDs, right? I can argue either way, and it depends. There's no right answer here, but this is a real thing, right? So first, kind of even talking about sensitivity, you get into these kind of questions. Let's talk about budgets. Privacy budgets, our favorite things, right? Whose favorite things? Privacy budgets? 1, 2, great. So we talked about privacy budgets. Ideal view for differential privacy of an analyst workflow is you have to compute the mean or the sum statistic. Here's a bunch of data. Here's my new mechanism that computes it better than your mechanism. Aha, I'm better. This is not how workflows work, right? An analyst workflow says, I get a data set, now I'm going to explore it for a while. I'm going to compute different statistics, I'm going to look at different projections, I'm going to run different queries against it, and so on and so on and so forth. First, who pays for that exploration, privacy-wise? Right? Now, we can argue that maybe you shouldn't pay for it because that's not shared later. Again, we can argue, but there's no clear answer. Right. The second part is that even once you've done it, you're going to be debugging these SQL queries, right? Somebody else is going to be debugging them. Maybe some analyst said, these are the statistics I need to produce. Somebody else is now implementing it. They're going through the same questions. And then it turns out the world changed overnight. You need new statistics and so on and so on and so forth, right? So what do? You can close your eyes and pretend this doesn't exist. Right? And you can somehow argue that these are not subject to the DP guarantee because X, Y, and Z, but this is, again, why, right? What is it that you're making your argument saying, this is okay, but releasing this data or doing something else is not okay? You can make that argument, there are real arguments to be made, but it's not entirely clear. Or you can track your epsilon budgets as it grows into double, triple, quadruple digits, but then what does that mean, right? What have you accomplished? You haven't accomplished nothing, but let's be honest about what you've done. Right. And again, this goes back to this question. We do not live in a DP world. There are some parts that are going to be deterministic. Right? And so our infinite epsilon sort of right off the bat. They might be as minute as storing the size of your database on disk. Right. Now, I think we would all agree that this is not an attack vector. And we would probably be wrong because somebody somewhere is going to figure out a way to say, no, if I knew how much data is stored on disk, I could figure out whether XYZ did something else, right? So how do we think about these things in a place where there's a mix, right? This is precisely what we wanted to avoid thinking about. Like we want to be computer scientists doing math, right? Like we don't want some of us, right? We don't want to be thinking about the nuances of saying like, what is the actual attack here and doing the policy side, unless you want to do it, right? But for us doing math, we don't want to think about it. And yet, if you are trying to do differential privacy in practice, you absolutely have to think about it. There's no running away. So this is budgets. And we can talk about time here, but I'll save time for my third point, which is neighboring definitions, right? So you go to differential privacy, you face a stark privacy utility trade-off. You can say, well, Sergei, I don't want to make my epsilon to 100 because you already will make penalty for that. So that's not going to work. So I'm going to change my neighborhood definition. This is a reasonable way to do it, right? It's a way to increase your utility because you're reducing your the set of the constraints that you have to set. And you retain your mathematical guarantees. Right? Some of the examples here that are very common. The first one is time. Okay? I'm going to run the same job daily. It's going to go over parts of the data set that are repeated, right? Some of the parts of the data set were present yesterday and they're present today, but I'm going to count the epsilons as different. Right? I'm almost going to look at an epsilon rate rather than epsilon sort of correlate. Is this reasonable? Well, formally, no. Right? Formally, you should add them up. We do this all the time, and it's not just we, Google, everybody does this all the time. Right? If you're doing this in practice, jobs don't run once, they run all the time, regularly. Right? IDs, right? Ideally, differential privacy talks about a physical, natural person. I don't know who the natural people are, so we can look at cookies, we can look at some other IDs, we can look at phones, we can look at Metro card swipes, you name it. There's not a one-to-one mapping with the IDs. Moreover, this goes the other way. The people who are really worried about their privacy usually will have multiple IDs, right? And the more worried they are, the more different sort of persona they will have and the more IDs they will have. But from our standpoint, they'll be different people. And so we will give them less protection, even though they're trying to get more protection. Again, just a thing that happens in the real world and something that we have to worry about. I'm going to go into a little bit more details on labels because it's just kind of illustrative a little bit more to say when we're doing machine learning, we're looking data releases for machine learning, there's this notion of label differential privacy, where you have your features that are public and your labels that are private, right? And now what this allows you to do, as with all of these others, is that you can write syntactically formal definitions of differential privacy, right? Here's a neighborhood definition, here's a sensitivity, here's my mechanism, here's the definition that I've achieved. But the question that you forego is, what is the actual semantic privacy that you're providing, right? Because there's maybe many IDs, because there's something else that's going on. And again, we have to go back and think about it. It might be absolutely the right thing to do, and it is the right thing to do in many cases, but you have to convince yourself, or you can have to convince somebody that this is a reasonable risk that you want to take. Right. So let me talk about label DP just for a second. So from the literature, right, what is label DP? You have example records, right? So we have Alice through Harrison here. They all have a feature. Here's a feature, it's going to be a single natural number, and they're going to have a label. And you can see what the rule for the label is, right? Negative numbers have a negative label, positive numbers have a positive label. Great. So now I'm going to say the label is private. So before releasing this data, I'm going to do randomized response on the label. So I'm going to flip some of the labels. You can notice I flipped 2 of them. And now I would say, hey, this is a private release. I've flipped 2 out of, I think, 8 labels, so my epsilon is actually pretty low. I'm in a good regime here. Am I? Because what the attacker is going to do is the attacker is going to compute a model, right? I can regress on the labels, you can do anything you want, I'm gonna find a separating line that's around 0. I might be a little bit off. And now, as an attacker, I have a Bayesian update. I can say, hey, my machine learning prediction says that Bob should be negative, but Bob is positive. Now, is it likely that my machine learning is wrong? Or is it likely that the mechanism flipped Bob? And what is the Bayes update going to do? It's going to change the epsilon, the effective epsilon. And what you can show formally here is that there is this dichotomy that sort of either you can learn really well, or you're providing privacy. Now, some of you should vehemently disagree with me here, right? On is this a privacy violation? So far, nobody wants to speak up, but I'm sure a lot of you are thinking, Sergei, please, the very first thing that's written in the Dwork and Roth book is that inference is not a privacy violation. So this is not a thing. Please stop, go somewhere else. So this is from Fermat's last theorem. So you know, I'm running out of time. The margins are not big enough here of time, but suffice to say, reasonable people can disagree. I'm happy to have very long discussions about this because that happened before. But I'm not going to agree with everybody in the room on whether or not this is a privacy violation. So this brings us back to the survey. Now recall, in the survey, I believe one person bravely voted for candidate 2. And at least a dozen people said, I'm going to release my data with differential privacy, epsilon of 10. You know where this is going. So we're going to do randomized response with local DP. So if you release your data with randomized response with local DP and epsilon of 10, the probability that you lie is less than 1 in 10,000. Now again, do you have some plausible deniability that you lied? Yes. Is it going to stand up when I publish this somewhere else and says, you know, so-and-so did this terrible thing? Maybe. I don't know. And so is this protection better than anonymity? Maybe. Now, some of you had assumed, I think, that when I said epsilon equals 10, I'm doing something else. And I think Rachel pointed out and said, but what are you using, right? And I said, that doesn't matter. You have epsilon equals 10. Right? So now what? I don't want to say that, you know, we're stuck or that differential privacy is bad. On the contrary, I think it's really formed our thinking and really advanced what we can do and actually shape the conversations with the regulators. It shaped the conversations with product people. It's allowed us to actually make formal guarantees about what we're doing, right? But this trade-off between really formal definitions and the utility that you're going to get is real. And I think that we can, there are bad ways to try to address it, which sometimes are easy to do and we want to do for whatever reason, right? We can increase epsilons to the point that it's absurd. In the previous example, if I just talk about epsilon equals 10 is absurd, right? I will die on this hill. For randomized response, it doesn't make sense. Right? Maybe somewhere it makes sense, but it's hard. It's hard to argue that, right? We can avoid accounting of some operations and say like, oh, this is not part of the DP accounting that we want to do. Look over here, here everything's perfect and DP with some low epsilon, but over here just don't look and this is fine. I don't think that's the right way to go, right? I don't think we want to rely on formalisms to say, oh, well, you know, formally I have this syntactic guarantee that's rigorous, but then it falls apart when I go to real world data. What do I do then overall, right? Or just pretend that these trade-offs don't exist, right? I don't think this is a good way to go. I think we are going towards the right direction though. One is, of course, the smaller the trade-off, and this is what we're doing day and night about just getting better algorithms, better mechanisms, the less this matters, right? But sometimes we have optimality. This is as far as you can get. You know, there's information theoretic lower bounds or something else that's good. And so my view on the same problem that I think Shannon pointed out is that we need to bring some rigor to this reasoning about beyond worst case of differential equations. Right? It's hard. I think many people have tried before, right? I think one of the things that falls apart is the composability property. That's actually key to everything that we do, right? And so, but we shouldn't give up just because it's hard, because this is going to be the thing that actually moves the needle overall and allows us to talk to regulators a lot more. Because sometimes, as I think was pointed out before, the regulators come back and say, yes, this is a nice formalism. I care about this risk. How do they compare? And they often over time say, this is too worst case, right? And I think we pride ourselves on being worst case, and it's gotten us far. But if we want to go further, we have to go beyond, and we have to find a vocabulary to think about it. That's it.